this polynomial only works with constant coefficients. Again, on exams, people forget, and I've seen things where there'll be a variable coefficient, and then they'll put x in there, and then they get r as a function of x. But that's completely against what we did. When we did e to the rx, we assumed r was a constant, not a function of x. Okay? So, yeah.
In that, where R2 equals R3 equals 2,
yeah.
That would be the k is 2.
Case 2,
right?
yes, exactly.
So you can't do e to the r1x and then x squared e to the r1x.
No, be careful, be careful. Remember, how you label the roots is immaterial, okay? Some other person may just, they may say R1 equals 2, R2 equals 2, and R3. The subscripts are completely immaterial, okay?
No,
the important thing is that you have 1 is a root of multiplicity 1, right? So you don't do x e to the x. It's only becomes 1. So that's why you get C1 e to the x. We have a double root of 2, and that's the one that you have to do x, e to 2x and x e to 2x.
But the very next one you have to go x. You can't go x squared, right?
That's right. Okay, what would happen though? It's a good question in the sense, basically, suppose we had a fourth order equation, and we had a root of 1, and 2 is a root of multiplicity 3, that you're talking about. Then you have the e to the x, e to 2x, x e to 2x, then x squared e to 2x. Yeah. Yeah. No, if you just made this x squared e to 2x, it would not be, check it. It was not a solution. Okay? And the reason is, to go back to theory over here, it comes back to this, because you can only factor out over here the multiplicity. Right here was a double root. Okay? And then when you do that thing, you differentiate twice, it falls apart. Okay, so we only have one more case to do, complex roots, right? Then we have the whole story. Okay. We've got root of multiplicity over here. Okay, let's do case 3 over here. So case 3 basically is a case where you have a complex root. And like I said, that can certainly happen, even though this polynomial that we get all the time, this characteristic polynomial, has real coefficients. It doesn't rule out the case of having complex roots. Before we do complex roots, though, we have to derive something that's usually take us in complex variables, but we need this piece of information over here. It's called Euler's identity. Okay, maybe you've seen some T-shirts that have MIT has this T-shirt with e to the I pi equals -1 and stuff like that. Okay, it's one of the famous identities of applied mathematics, and we're going to derive it now. It's called Euler's identity. My derivation over here is going to be purely formal. Okay, in other words, a really careful mathematician would have a lot of objections to this because I'm going to do stuff formally with series and stuff like that. But for engineers, I think it's good enough. Okay. Euler's identity. Basically what I do is get a formula for the exponential of a complex number. Okay? Well, does that mean anything, and how can you do it? Okay? And the way we're going to do it is we're going to start off with the series that everybody knows for the exponential. I'll call it e to the z. Okay? And your calculus book was probably e to the x. Okay? I don't expect you to remember it, but basically, if you remember Taylor's formula, you can derive it, or you can just look it up. The series for e to the z is the following. It's 1 plus z plus the z squared over 2 factorial plus z cubed over 3 factorial, and keep going, right, plus z to the n over n factorial, That's the general term. That's the exponential function. Expand as a power series. And you can show that that series converges for all values of z, considering real values of z. Okay. What I'm going to do now is replace z by I theta. Well, everybody knows about I, right? Where I squared is -1. Okay. So let's replace z by I theta and just formally crank out what we get. What's e to the I theta then? It's 1 plus I theta plus, be careful, it's I theta, the whole thing squared, over 2 factorial, plus I theta, the whole thing cubed, over 3 factorial, plus, and go one more, I theta to the 4th, over 4 factorial, So all I did is replace z by I theta. Okay? And we all know the property of I, right? I squared is minus 1, and therefore we get any power of I. E to the I theta equals 1 plus I theta, right? What happens to over here? You get I squared, which is negative 1. So that becomes minus theta squared over 2 factorial. What happens over here? We get I cubed, but I cubed is I squared times I, which is a negative I. So you get negative I theta cubed over 3 factorial. What I'm doing is I'm just separating the reals and imaginaries eventually. Okay, plus I to the 4th is easy. It's I squared squared, which is plus 1. So your theta 4th over 4 factorial plus dot, 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 dot. Let's get all the reals and imaginaries together. E to the I theta. Let's collect reals. We get a 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus dot, dot, dot. Okay, you can do that. Keep going on. The next one is obviously minus theta to the 6th over 6 factorial. And now let's pull out everything that has the imaginary unit on it. I get a theta over here, right? Minus theta cubed over 3 factorial. And if you did the next one, it would be plus theta to the 5th over 5 factorial. Dot, 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 dot. And again, going to infinite series, if you go to a table, or if you remember, it comes out that this is the infinite series for cosine theta, and that's the series for sine theta. And they converge for all values of theta. So, proceeding formally, at least, I find that E to the I theta is cosine theta plus I sine theta. And that's the formula that I've been looking for. It's called Euler's identity. Okay. Let's just put a little red box on that. Okay, this is Euler's identity. Okay? And we're going to need that little piece of information when we do case 3 of complex roots. Case 3, complex roots. Now what's going to happen in the case of complex roots, because the characteristic or the auxiliary equation has real coefficients in it, well, you know, of course, we're always doing basic differential equations where all the a's are real, x is real, y is real, they're going to occur in complex conjugate pairs. So you can find out that it's 5 plus 8i is a root, 5 minus 8i is a root. That's always going to happen. Okay. So let's just take, let's concentrate on the complex roots. Again, in general, you have a polynomial of whatever degree. You know, some of the roots will be real, some of them will be real and repeated. Now we encounter a complex root. But we know they occur in pairs, okay? So I should say over here, since the auxiliary equation, I only say characteristic because I can't spell auxiliary correctly. Since characteristic equation has real coefficients, complex roots will occur in conjugate pairs. And you'll see this when we do examples also. Complex roots always occur in conjugate pairs. And again, hopefully I'll remind you what conjugate means. Conjugate pairs. So it will have basically roots of the form alpha plus I beta. That's the second one group. And the second group that will occur is alpha minus I beta, where alpha and beta are real. So you may get root 2 plus 3i, you will always get root 2 minus 3i. And these are called complex conjugates because they're imaginary parts. One is plus beta, one is negative beta. Okay? So there's going to be two solutions corresponding to that. Okay? Okay. So what we're going to do again is proceed formally. Okay? Let's use case 1 over here. And because alpha plus I beta and alpha minus I beta will be different, right? Unless beta is equal to 0. If beta is equal to 0, then it's a real root, so we know what to do. Okay. So obviously we can say over here beta not equal to 0. If beta is equal to 0, we we got just a double root, we know how to do that. Okay, so we got real, we got complex roots over here, and we have to know how to handle that. Let's just proceed as we did in case one. Well, case one said that if you had two roots and they weren't equal, one solution was e to the r1x, and the other one was e to the r2x. Let's just use these values for r1 and r2 and see what we get. So we get a constant c sub 1, e to the power of alpha plus I beta x, that's the first guy, plus another constant c sub 2, e to the r2x is going to be e to the alpha minus I beta x. Okay? Now, we should make a note over here. These are complex numbers when I do e to the I beta x and e to the negative I beta x. Remember Euler's identity? They generally be complex. So C1 and C2 will be complex. And you don't want to express solutions to differential equations in complex form if everything is real. Right? We want to work this out so we get real solutions, nothing with i's in it. Okay? So, since y of x is real, it comes out that C2 is the complex conjugate of C1. We'll just put a bar over that. It's like, for example, if C2 was 6 plus 8i, the other guy would have to be 6 minus 8i. Okay. See, you don't want to leave it this form where you got complex coefficients, you got complex exponentials. Let's just kind of see if we can get this actually into a form where everything is real. Okay. So here's what we're going to do. Y of x equals, okay, c sub 1, right? Remember your rules for exponentials, right? E to the alpha plus I beta times x is e to the alpha x times e to the I beta x. And again, if you haven't taken a course of complex variables, you just have to take this on faith. It's an extension of what you know from real cases, right? E to the a plus b is e to the a times e to the b, right? It comes out that when it's complex, it's also defined to be that way. So it's e to the alpha x, e to the I beta x, plus c sub 2. This one goes to e to the alpha x, e to the negative I beta x. E to the negative I beta x. Okay, to simplify this, let's pull out an e to the alpha x over here. Okay? Well, then I get c sub 1 exponential of I beta x plus c sub 2. I already pulled out e to the alpha x, e to the negative I beta x. Now you can see why I derived Euler's identity. Because we have to expand now e to the I times a real, right? Beta is real, x is real, so use Euler's identity. And here it's just a negative back, okay? So let's use Euler's identity now to write this in expanded form. And you can see what's going to be happening. What's interesting is that so far we've always had exponential solutions, right? Or x times an exponential. We're going to start getting sines and cosines now. And that's not surprising. Many differential equations have solutions to sines and cosines. So you get e to the alpha x. Let me write it like this now. C sub 1. Be careful now. Now what's e to the I beta x? Cos beta x plus I sine beta x. So we'll write in parentheses cosine beta x plus I sine beta x plus c sub 2, okay? Now what's e to the negative I beta x? You just have to remember the cosine is an even and the sine is an odd function, so we get cosine beta x again, and then we have I times the sine of a negative beta x, but that's just minus I sine beta x. Close the bracket. Go down here, y of x, almost there, is e to the alpha x, right? Okay, let's get all the sines and the cosines together. C1 cos beta x, C2 cos beta x. So C1 plus C sub 2 in parentheses, right, times the cosine of beta x. Okay? And then let's get the sine beta x stuff. I guess I could pull out a unit I over here, right? We get an IC1 sine beta minus IC2, so it's minus C sub 2 sine of beta x. Okay? Now, do we have everything in terms of reals now, or do we still have imaginaries? Let's see what goes on over here. Remember, C1 and C2 were complex conjugates. I have that right over here, right? What's a number plus its complex conjugate? It's real. Take 2 plus 3i and add 2 minus 3i. Right? The imaginary part cancels out. So this actually is a real number. Great. So now we have a real times a real, right? What happens over here? You have a complex number minus its complex conjugate. That's a pure imaginary. Again, take 2 plus 3i and subtract from that 2 minus 3i. You get 6i. But then the I hits an I, becomes real. See? So this one is a pure imaginary, but when you hit it with an I, it becomes real. Okay? So we can summarize this in the following way. Okay? This will be case 3. Okay? Case 3, I'm just going to write the final result here without all the algebra in here. Okay. If we encounter a pair of complex roots, and like I said, you're always going to get a pair, okay, because the equation has real coefficients. If alpha plus I beta is a root, then alpha minus I beta is a root. So if we encounter a pair of complex roots, namely, say R equals alpha plus or minus I beta, they always occur in those cases, okay? Then, the corresponding solutions of the homogeneous equation are, then the corresponding solutions are e to the alpha x sine of beta x and e to the alpha x cosine beta x. And obviously, for the general solution, you hit those with constants and use superposition, right? Okay. And it makes sense that we should get 2, right? Because this is going to occur usually when you get a quadratic. You use a quadratic formula, you'll get a pair of roots. Okay, so when you have that alpha plus or minus I beta, your real solutions are e the alpha x sine beta x and e the alpha x cosine beta